6 hours.
Yeah, exactly. 6 hours later.
Yeah.
Good.
Yeah, no, I think so. Yeah.
Right. Well, welcome. It's my great pleasure to introduce Neil Lawrence, who's we've been trying to get him around for a while, and eventually the dream has become a reality. Neil is quite a central figure in the world of data processing, machine learning. He does a lot of work, interesting work in biostatistics, but all sorts of applications. And the types of methods we'll be discussing have all sorts of applications, and we'll be looking at how we can use that in Uganda later on. We've also had Checo, who's a doctoral student in the University of Tokyo, helping out with the practical classes. I just wondered, before I hand over to you, it's useful to just go through some introductions so we find out who everyone is and where we're from. So just to start off, I'm John from talking to technical science. Who we take it here?
So we are from the Department of Mathematics.
Daniel, AI
Ibrahim Bossa.
Great.
Ibrahim, corridor computing.
B2 Albert, student Masters of Data Science.
Faisal Biza, School of Economics.
The one is Martin Godwin, Department of Computer Science.
Biansi David, student Masters of Data Science.
This is Dr. Chiroba, College of Health Sciences, Department of Epidemiology and Biostatistics.
Moses Chema, Agriculture. Richard Kapulma, History.
Henry Kabir from Uganda Statistics.
Great. Excellent. So I definitely won't remember all those names, but I got an idea of the departments. I think we'll try and keep things fairly informal today. I don't know how far I'll get through this set of slides, but there's some, as you know, there's some practical stuff that we'll try and do. But what I thought I'd do is start by talking about linear regression and basis function models. So I think there's a variety of different backgrounds amongst the group. But I quite like going back through the fundamentals anyway. So hopefully if you've seen it before, I'll be presenting things with a slightly different twist to what you've seen before. And if you haven't seen it before, then that's good as well. So just hands up, I mean, how many people would say they're very familiar with linear regression? Yeah? So good, that's good. And then, so that means presumably you use it fairly regularly. Good. Okay, so, and some weren't familiar, which is also fine as well, because that's really going to be my starting point. I'm going to use linear regression to lead into Gaussian processes. So unless we go much quicker than I expect, we won't talk about Gaussian processes today, but they are the background, they give us the background to Gaussian process models. So what I've got lined up is just a sort of review of regression, and then I'm going to introduce basis functions. So how many people have worked with basis function models before? Just a show of hands. No? John? That's it? So that's good. So I'll try and go through that reasonably slowly. And then I'll be using maximum likelihood for the first part. And then I want to justify moving towards Bayesian interpretations of these models. And in the second part, I'll talk about the Bayesian approach. So let's look at regression. So I think regression's a really bad name, actually, because it sounds like, well, the reason regression has the name regression is because of this effect of regression to the mean. So regression to the mean was an effect noted by Galton when I think he was around 100 and something years ago. he was trying to predict the height of a child given the height of a father. And what he found was very tall fathers had children that were slightly shorter than themselves, and very short fathers had children that were slightly taller than themselves. And he, for a while, thought that this was an effect, but it's not an effect. It's just that extremely tall people are on the outside of a distribution, and typically their children tend to be not so extreme. So all the effects that accumulate to make someone very tall, like diet, genetics, so on, if they're extremely tall, it's quite likely that the next generation won't have quite all those effects. So you return to the mean, this effect called regression to the mean. And that's where the name regression comes from, because he used these least squares models. These models go back a lot longer than that. They go back to sort of astronomers who were trying to track positions of planets in the skies and using least squares results. But in statistics, that's where they came in. And they ended up with this name regression that comes from that effect. But I very rarely worry in my work, it's an important effect about regression to the mean. So in some sense, it's an odd name. And you might better think of this as curve fitting or line fitting or prediction, because the objective is to predict a real value given some inputs. So here's some examples of, this is an example, this so-called Tecator data, which is where they've got some, they do some analysis of meat. This was in Denmark. In Denmark, there's a lot of pig production for producing bacon. We eat a lot of Danish bacon in the UK. And so they have these automated systems for scanning the meat and trying to predict its quality. So the input there is some spectrum from a scanner, and then you're trying to predict the quality of the meat, which is rated on some scale. So input is the spectral measurements, and the observation is some quality of meat. Radiocarbon dating. So how many people are familiar with that term, radiocarbon dating? So yeah, it's based on the idea that across history, the level of carbon-14 in the atmosphere, if it had remained constant across history, then you can date the, if you dig up an animal or a tree, you can try and date that animal or tree by the amount of carbon-14, because it's decayed in the animal, that's left in the animal. So you sort of say, oh, well, it should be constant in the atmosphere. When this animal died, it took in that certain amount of carbon-14, but since it's been dead, that carbon-14's been decaying because it's radioactive. And you look at the percentage of carbon-14 and you predict a date for that object. It's a tree or an animal or a skin. But of course, in practice, carbon-14 hasn't stayed constant in the atmosphere. So there's been some variation over time. So there's a regression problem which is very well studied in Sheffield by Tony O'Hagan's group, which is to try and calibrate going from the radiocarbon date to the actual date. And they can find this actual date by things like, they have these histories of tree rings. They do this tree ring dating to try and calibrate the radiocarbon date. So that's another example of a regression with some input, some output. Here's another one which is slightly different, but it's quite interesting as well, particularly in backgammon. Quite a long time ago, the best computer backgammon player, people familiar with backgammon? I don't know how popular that is here. It's a board game. And it's one that's difficult for computers to play using standard AI techniques. So people came up with the idea of encoding the position on the board as a vector, x, and then getting experts to score the quality of the position on the board. So then they built these regression things to try and predict the quality of the position. So if it was chess, then you take all where the pawns and the knights and the queens and kings are, you encode that in a board, and then you make a prediction of the quality. An expert says that's a good position, and then you get the regression to make a prediction of the quality of the prediction. And that's treated as a regression problem. So I was going to use this example. So this is another nice one-dimensional input. So in some of those examples, the inputs, this is a one-dimensional input, x is one-dimensional, and y is one-dimensional, but in others, x is multi-dimensional. But because we're going to do a lot of plotting of regression, I thought to use this example that's particularly from a book by Mark Joalomy and Simon Rogers about the gold medal Olympics winning times since 1896, the first Olympics, 100 meters. But then I thought that actually 100 meters isn't a very serious event compared to a much more important event. So here's the data for that, by the way. So this is 1896. They took 12 seconds to run it. And this is 2012, Usain Bolt's gold medal winning time that was 9 point something. The 100 meters is a little bit short. It's not very far. I thought much better. It's a real sport. The marathon, which real men run, none of this short little jogs. And instead of doing that, so Stephen Kiprotich, of course, won in London, famously. But the marathon hasn't always been the same length. So early marathons were closer to 40 kilometers, whereas Stephen did a 42.195 kilometer marathon. So before 1924, they weren't standardized. So what we're plotting instead is the pace per kilometer. So this is Stephen Kiprotich's marathon in 2012. It's the second fastest in terms of pace per kilometer across all time. Of course, he ran it on a very hot and humid day for London, certainly a very hot and humid day. So it's slightly slower than the one before. But then you can see, as you go back over time, you have slower marathons. This is 1896, the first marathon. Now, so this is 4.5 minutes per kilometer. This data point's unusual because this was when the marathon was in St. Louis in the United States. And it was very badly organized. They made them run along dirt tracks out in the countryside, and the officials' cars drove with the runners and were picking up clouds of dust, and the runners were sucking in dust and stuff. So this is actually about the time I would do a marathon in. I mean, I wouldn't. It's just about achievable without all that dust for me to do a marathon at this rate. 5 minutes. It's about 5:15. That's a little bit faster than I could go, but it's achievable for regular people. This is down to 4.5 minutes. And then these times here are just incredible. I mean, I could not run a kilometer at this pace. It's an incredible pace. It's an incredible pace for 5 kilometers. This is my 5 kilometer pace. I do 5 kilometers about here. So we see, over time, people have got better at the marathon. And the idea would be, well, can we build a model to predict what the marathon winning time will be in 2016. So our inputs are the year of the gold medal, and the output is the pace in terms of minutes per kilometer. So that's our data. So now I just want to talk briefly about what machine learning is. So that's at the core of, I think, a lot of things we're interested in. So what gets me going about our field is intelligent analysis of data. Data is all around us, particularly now with things like the internet, with mobile phones. I mean, we've just seen in the US and the UK, the amount of data they've acquired, the security agencies, enormous amounts of data. Now, I find that all very terrifying, but even ignore the security agencies, companies like Google, who are trying to do targeted advertising towards people, trying to predict what people are interested in. Data's everywhere now. Now, my feeling is you can't say anything just given data without making some assumptions. So I feel data on its own is next to useless. What you need is data plus a model. And the model encodes what you believe about the world. So there are certain models that we feel are naturally sensible. So we often encode things like smoothness into a model, and we're going to start actually by encoding linearity into a model. So it says something about how we expect the data to combine with our belief about how the world works so that we can make predictions. Why do we need a model? Well, data on its own is just data, and it's my strong belief that if, for example, going back to the marathon timing data, if we don't make any assumptions, we can't make any predictions. All we can say is what the pace was in 2012, 2008, 2004. We can't say anything about it between those years. And I think that that's quite reasonable, that if you just have the data like this, you might look at it and think, well, I would expect it if they did an Olympics in 1982, that the time would be around 3 minutes per kilometer, because you can see the data here. And we might all feel that's a reasonable expectation. But when you make that prediction, you're introducing assumptions. It's not in the data to say that. The data does not say that. All the data says is at specific times, at specific days, these were the times. I mean, reasons why you could be wrong could include things like this. The fact that on that particular marathon, they had these cars throwing up dust, and it was very, very difficult to even finish. In fact, I think only 5 or 6 runners have recorded times for that year. So lots of runners didn't finish. So you don't know that that's not happening. You don't know what's going to happen in the next Olympics or whatever. So you can make a belief, but you can't know. And in order to have a belief or make a prediction, you have to have a model. And the prediction is what we're interested in. So the prediction is any kind of result. So an action to be taken, a categorization, for example, or a quality score, or a prediction of a future time. Prediction could be any sort of thing. Given the data, we combine it with the model. And the model could be much more complex than the sort of things we'll look at today. But those are the sort of 3 components. We want to make predictions. We can't do it on data alone. That's my claim. You're always modeling if you're going to make predictions. So we're going to start with today is to model a linear relationship between the time, which is the input to the regression x, and the observed running speed. So y is the winning time, or the pace in the case of the marathon data. And what we're saying is that it's equal to the time, the year, that it occurred, times some coefficient m plus some offset c. So x is the year of the Olympics, and m here has an interpretation of a rate of improvement of the marathon speed over time. So it's got units of something like seconds per year. So or minus. It would be a minus probably because presumably people are getting faster, and it's in units of seconds per year, how much quicker marathons are getting. And then C is the offset, and C has the interpretation of what the winning time would have been at year 0. Because of course if we put x equal to 0, so this is the marathon run in the time of the birth of Christ, then C tells us what that marathon time would have been. Yeah? It extrapolates back. Of course, there's all sorts of assumptions, and I doubt it's going to give us the right marathon time, but that's what the interpretation of these parameters is in the model. So how do we fit these models? And I'd like to sort of go back to basics. That these methods that we're using were first proposed for astronomers around 200 years ago who were interested, they had Newton's equations. So they now understood that the planets moved in a predictable way, but they were interested in finding out what the parameters that determined the orbit of those planets were. So there's a famous planet called Ceres that was discovered in about 1801, and it was seen in the sky, and someone made some observations of where the planet was, but the bane of all modeling is people keeping their data private, and this is true today. So the person who discovered the planet, he was a Sicilian, well, he wasn't Sicilian himself, but he was working in Sicily. He knew it was a new planet, or believed it was a new planet or a comet, and he wanted to be known as the discoverer. But to be known as the discoverer, he had to predict the orbit. So he tried to predict the orbit, but he failed, and he hadn't released his data. So by the time he got around to releasing his data, because he realized he couldn't predict the planet had moved on in the sky, had moved behind the sun and disappeared. So the planet was lost. But Gauss, who was a very young mathematician at the time, I think about 21, he took the data and he applied the methods we're going to talk about. It wasn't linear regression because it was a basis function based model, to predict where this planet, Ceres, was going to be. And he predicted its position a year later. And they were able to recover the planet and find it was, well, they named it Ceres. It's a planet that's between Mars and Jupiter. And you might be thinking, why haven't I heard of this planet? Well, that's because it turned out to actually be a large asteroid. It's part of a large asteroid belt. And it was reclassified as a dwarf planet very recently when Pluto was moved to be a dwarf planet. But the techniques that Gauss used were the techniques we're going to talk about. But the challenge he faced, so there were, I think, 34 measurements. This guy Piazzi, he took 34 measurements of the planet in the sky over a month and a half. So he observed it on New Year's Eve, I think 1801, and then he observed it until February, with some observations missing because of clouds. So he had 34 measurements, but within the model that they had, there's only a couple of parameters. So the easy thing to do is actually, so mapping this back to our sort of problem, if we have just two times, so this is I think 1904 and 1984, of what the marathon time was, then we know how to get these parameters, M and C. Because this is a system of two simultaneous equations with two unknowns, yeah? So what we do is we subtract one equation from the other. This is the first time I've done this in, well, myself, because of course the computer's doing this for me all the time. But the first time I've done this in, since I was at school to do these slides. So subtract one equation from the other, and then that causes C to cancel, yeah? So then we get y1 minus y2 is equal to m times x1 minus x2. And then we say, okay, let's just put the x1 over minus x2 on the other side, and then we get a result for m. Given a result for m, we can then substitute in, we can say C is equal to y1 minus mx1. Oh, and just the result for m is represented by this. It's basically that distance over that distance. That's why it's the gradient. And then C, we can just substitute in m to recover the result for C, which can be visualized if you go back to year 0. You'll see that their time was extremely slow. Okay, so that's great. But how do we deal with a third observation? This is the challenge facing people who are trying to fit these models to data. So we've now got what we call an overdetermined system, because there's two unknowns, m and c, and three equations, because we've got a y1, a y2, and a y3 now. So how do we deal with this? So the additional observation leads to an overdetermined system. And what I want to introduce is, this is, I would say the person who first saw models like this wasn't Gauss, it was Laplace. Laplace is a famous French mathematician, astronomer, physicist. I mean, they were just amazing at that time. And what he considered, his theory of error was that the reason that you have these small perturbations of the planet's position away from the truth is because of errors in your measurement brought about by the poor quality of instrument. And that error is unknown. So if the model is correct, this cross should land on this line. Yeah? If the model is correct. But the point is the model isn't correct. And so for each time point, you add some noise corruption. The theory of error says you should add some epsilon, where epsilon has the same index as your data, but you don't observe it. So I see this as what we'd call a latent variable. It's an unobserved corruption of the model that is causing this point to fall off the line. So this noise model gives the mismatch between our true model and the data. Now, I'll come back to the Gaussian in a second. But it gets around this being the problem. So if we have a third data point, there's three possible lines we could fit. Yeah? But we want one line. And the way we deal with that is we have this epsilon being added to each of these equations. So these just happens to be the data. So we have three simultaneous equations plus an unknown. But how do we deal with that unknown? Well, what we do is we say that this unknown is drawn from a probability distribution. And in fact, Laplace put an enormous amount of work into working out what that probability distribution should be. He did an enormous number of calculations. He had, I never remember, his principle of insufficient reason, which is just the most amazing thought for someone 200 years ago. It's basically very related to something we use today called maximum entropy, that says that if you are in a position where you don't know something, you should maximize the sort of uncertainty associated with it. Now, when he tried to do that for these error functions, so the problem with these error functions is what you're saying is you've got some corruption, and then we're saying on average, in this case it's 0. It could be biased, but then we could just add that bias to C. So if there was a bias, we would put the bias in C. So typically we'd think of the corruption as being distributed along the same axis as y, so it's epsilon, but it's in the same units as y, and then the corruption for each measurement will be distributed in some way. So you might argue, well, this is going to be potentially symmetric, and that you'd expect most things to be close to the mean and other things to be far away. And Laplace tried to build arguments that maximized the sort of uncertainty associated with this distribution, but it led to some very complicated densities. And he had this trouble that he couldn't do the maths necessary to solve the system. So Gauss's contribution, and Gauss didn't invent this distribution, but the reason why Gauss's name is associated with this distribution is Gauss suggested that the normal distribution is used here. Now, in some ways, I mean, Gauss did many wonderful things, but in some sense this wasn't that amazing, because he wasn't necessarily the first to use least squares, although he claimed he was. Other people suggested the algorithm that follows from using this density, and he didn't really give much theory as to why this density is a good one. Why is this density a good one? Well, you can justify it by appealing to the central limit theorem. So we'll come back to the Gaussian density in just a moment, but that's one justification. It's also a really good one to use because it leads to a very analytic solution, as we're going to see. But you can also use other models. So I've roughly drawn a Gaussian here. A student T is a model which allows much larger corruption. It has heavier tails, so you can get measurements a long way away from the mean with a student T, and that's something you can use for robust regression. We're not going to talk much about that in these lectures, because we're going to mainly focus on Gaussian. Gaussians turn out to get us a very long way, even if they're not always correct. So the Gaussian model is the model, I would say, for the error in our model. So there's the world, and then there's what we're saying about the world, which is a linear regression. And then the Gaussian model is giving us the difference between the truth and our model. Yeah? And that's what we sometimes call noise. The term noise is, of course, coming from things like signal processing. They called it theory of error, I think, the physicists who worked on this, because, of course, it was the error, the model error. But that's where the Gaussian first comes in. Any questions at that point? Yeah?
Where does the term overdetermined come from?
Overdetermined. It's because, I believe, I'm making up my answer here, but I think it's a reasonable one. It's because those equations determine your parameters on their own, and a third equation gives you too many equations, so you're over-determining your parameters. Because in contrast, as we'll come to later, you can get underdetermined systems where you don't have enough equations to determine your parameters. So overdetermined in this sense means that because there's three equations here, we get these three different possible linear regressions if we don't include the noise model. And actually, they did all sorts of cool things. They used to fit. Before they came up with the theory of error, they used to fit all the possible linear regressions, and then they would look at the parameters and perhaps look at the median and then select the one with the median parameters, stuff like this. So they had these techniques. They actually used to, before they had, before Laplace and Gauss, fit every possible combination. So they had like 17 observations, 4 unknowns, and they'd try and fit them all. And of course, the difficult thing in those days, the theory was quite simple. What was really difficult was the mathematical operations that you needed to do to extract the parameters. Even for straightforward linear regression with a number of observations, you've got well, with multi-dimensional inputs, you've got a large system to solve. So they had to do a lot of maths to try and solve these systems.
Question. So would you please just recap? So the Gaussian model takes care of the model as well, plus the error, or only the error?
I'd say, so at the moment, I'm saying that the Gaussian model is only taking care of the error. So we've got a model which is deterministic. Now we're going to change that. But at the moment, it's only taking care of the error. But in some sense, and I know this isn't necessarily the statistical view, but I tend to think of, I find it easier to think of, where's the best equation? Perhaps one of these. I find it best to think of, oh no, it's not there either. Here, let's take this equation. I tend to think of this as the model. Yeah, that includes everything. It includes a deterministic part and some assessment of what's going wrong in the world. Now, a lot of the time people think of this noise model as a special case, and that's because they're typically assuming that noise is to be independent. But I tend to think, actually, let's build a probabilistic model for everything. But we're not doing that yet. For the moment, we're saying we've got a deterministic, what's in our head about the way the world works is a deterministic part. And then the only stochastic part is the departure between the way the world really works and way we think it works. But we'll change that before the end of the day. Okay, so the Gaussian density, so it's perhaps the most common probability density. It's so common that I think even people think that features of that density are features of all probability densities, and we'll look at a couple of the features of that. It's core to everything we're going to talk about. It has some remarkably unusual properties which no other distributions have. In one dimension, it's specified by a mean and a variance. Now we said the mean of the noise is 0 in the linear regression model, so that actually means that we're saying that the mean of the whole system will be given by mx plus c, because it's mx plus c plus this noise. So we'll see that, we'll write that out in a moment. The other parameter is the variance, which dictates the width of the density. And this is what it might look like. So here we've got a Gaussian density which roughly represents people's heights. So it's got a mean of 1.7 meters and a variance of 0.225. So that means that we can visualize the standard deviation, which is the square root of this, which is actually in this axis here. So the standard deviation is something like that amount. I can't square root that in my head at the moment, but I should have remembered what it was. It would have been better to write down the standard deviation, but it'd be something like, I don't know, just under 0.5, isn't it? Because 0.5 would be 0.025, so just 0.4 something. And I took that roughly off populations. So this would be a good density for the height of men, for example. And that's the sort of thing people use Gaussians for. When I was at school, I used to find Gaussians thoroughly boring. For a long, long time, I thought of Gaussians as almost the most boring thing you could do. Why? Because when I was at school, they made us do a lot of adding up numbers and dividing them by the number of numbers to compute the mean. And then doing another formula to compute the variance. And I hated that maths. It was, maths to me was all about being really sort of having to manipulate equations and stuff. And that was the one bit of maths where you just had to remember it. So I hated statistics as a result. Now statistics has a lot more interesting things in it than that. But when you're at school, that's what they teach you for statistics. They teach you about the Gaussian. And we used to have to look up the integral of the Gaussian in a set of tables. So we would compute the mean of a population. We would compute the standard deviation. And then we had a set of tables. And then we would be asked, oh, well, someone's got a height of 2 meters. You know, in which percentile is that? So you would then look up in the table and you would find that it's, you know, in the 97th percentile for this distribution. So I didn't really like that type of math. So it's ironic that almost all my research now centers around Gaussian distributions. Be careful what you dislike. Okay. So it has some really remarkable properties. They're the sort of properties that I think you learn or you know about, and then you just don't assume they're special, and it's only when you try them with other distributions you find out that it doesn't work. So the sum of Gaussian variables is also Gaussian. So the sum of yi, where yi is a Gaussian distributed variable, if we want the sum of them where I equals 1 to n, then the mean of that is also Gaussian, and it has a mean which is the sum of the means and a variance which is the sum of the variances. Now, the fact that the variances sum is very important, and this is something that the old physicists before Laplace didn't really fully appreciate. What they thought when they had this overdetermined system, they thought that what you should try and do here is find the 2 best measurements. Yeah? You should find, you know, 2 of the measurements were the best, and you should try and work out which they were, get rid of all the others. Because putting all the measurements in, that just seemed philosophically wrong, because some of them would be adding to the error. So they had this sense in which when they thought about it, they said, no, we don't want to use all 17 measurements. We want to find the 2 most accurate measurements and use them to make the prediction. If we use all 17, we know that we're just adding corruption from these 17 measurements. But the fact that these, I mean, it's related to the fact that these, this equation here, because the variance is sum, if you keep measuring something and you have the same noise on it, every time you measure it, if you look at the sum of your measurements, it will be distributed like this. But because if you want to then look at the average measurement, if you divide by n, you'll get a mean which is the average mean, and you'll get a variance which is the sum of the variances divided by n. But the error in terms of the way you perceive it is not the variance, it's the standard deviation. So the standard deviation is what we plot on here, the standard deviation. But because the variance is sum, the standard deviation of the end result of all your sum is the square root of this. So the standard deviations go up with square root of n. So as you keep taking measurements, your error drops. It doesn't get worse. And that's actually completely embedded in all of us. Today, we always take more measurements. We don't have a problem with that. That's the nature of our work. But it's really interesting that there was a long period when they felt that that would be the wrong thing to do. Because taking extra measurements just meant you were measuring other corrupted things. You should find the best measurements. But it's because of the way that these measurements sum up that things go, you get the sum of the variances, not the sum of the standard deviations. If you got the sum of the standard deviations, then you would never decrease the error. And that property of the Gaussian is really important in the fact that we need more data in order to sort of, I mean, a load of statistics is founded on that. Now, one way that you can tell this is not true for any other density is the central limit theorem. The central limit theorem is used to justify the use of a Gaussian as an error model. And what it says is if you have y as not Gaussian distributed, so y is coming from some other distribution, as long as that distribution is finite variance, and that sounds like a funny thing. Finite variance means that, you know, the variance converges. You think, well, everything has finite variance. No, there are some distributions that don't have finite variance. Then the sum of those distributions actually converges to a Gaussian. So even if you do this for other variables, so binomial or Bernoulli or gamma distributed variables, if you add them up, the central limit theorem tells us that eventually you get a Gaussian anyway. And that sum can converge really quite quickly. So it can only be sometimes only about 6 or 7 things you can sum together, and then they'd start looking like very Gaussian. It depends on the variance of the different things, how quickly that converges. Now, Laplace was the first person to prove, I think he was the first person to prove a variant of this. In fact, you use the characteristic function, which is also known as a Laplace transform, or in some variants, or is that the moment generating function? I think the moment generating function matches the Laplace transform in order to prove this. And that justifies why it's also a sensible measurement error. So when you're taking your measurement of the star, there are 6 or 7 reasons the measurement's corrupt. One, because there was some oscillation, because the room moved, and another because of, I don't know, the atmosphere, and all these things were non-Gaussian distributed. If the corruption is additive, then the end result is often Gaussian distributed. Now, there are many, many cases where the corruption won't be additive, but it's as good a justification for Gaussian as any, right? So the central limit theorem means that everything converges towards Gaussian. So this can't be true for any other variable because of that. That's not quite true, because for gamma variables, gamma distributed variables, which are positive constrained variables, if they live on the same scale, they sum. The sum of 2 gamma distributed variables is a gamma distribution. But broadly speaking, that it also converges towards a Gaussian as it happens. That's why it works. It converges towards a Gaussian, but it's also gamma distributed the whole way. So this property is not unique, but it's rare, because other densities tend to move towards Gaussian when you do this. It's going to be important as well, because it becomes important when later on, next lecture, when we apply linear algebra to Gaussian distributed variables. Because we can combine that and the fact that scaling a Gaussian also leads to a Gaussian to mean that when we take a Gaussian vector and we multiply it by a matrix, we know the result of that is Gaussian, because the vector matrix multiplication just involves scaling and summing. So the result of the vector matrix operation is Gaussian, and the whole of Gaussian processes relies on that. That's why they work. The scale density is distributed as if we just scale by W, just scaling the mean and squared scaling the variance. Any other questions there? 07843. Incoming question from... That's great. It's like in auctions when there's someone on the internet. Okay, so this is what we think of as the likelihood of the data. So I've written f of x here to represent our model. So f of x is meaning in this sense, just because we've chosen a very simple linear case, f of x is equal to mx plus c. I mean, the next few days is mostly going to be about making this non-linear and more complicated. But this is generally true. Whatever function, so for example, when Gauss was trying to fit series and understand where series was going, his f of x was some combination of sines and cosines or whatever to make it an elliptical orbit. He was trying to fit an ellipse. So this is the likelihood, though. This is what we're saying about our data, that the mean of the Gaussian density is given by f of x. So instead of mu here, we have f of x, which is saying, in effect, that over... Oh, we have a rubber. I noticed this before there wasn't one. Is there a rubber anywhere? We can find one. I'll just draw a function sort of towards the bottom here. So what this is saying is that you've got your model of the way things are progressing, and this may be the carbon-14 calibration curve or the times of the marathon runners, but it's not going to be a deterministic function like that. It's going to be a deterministic function plus some noise. So we're getting Gaussian distributed. So what this says is that what we're observing is f of x plus Gaussian distributed noise. Y is got a mean of f of x, and then it's giving us noise of variance sigma squared on top. And this can be known as a process. It's a noisy function, a probabilistic process. So this is the type of models we will be mostly using, where y is given by some function of x plus some noise, and the noise is Gaussian. So here's the best fit sort of line for a series of data. So we can take a bunch of crosses and we can try and fit a line to the data, and we're going to do that in Python in a moment. And for our model, this is what we'd call the likelihood of an individual data point. So what Laplace proposed doing, actually he proposed doing something slightly different from this. But what he proposed doing, I mean, that's another feature of Laplace. Why did Laplace was very interested in probability before he was actually interested in this measurement of error. So he became interested in probability in terms of computing about games of chance, like dice rolling. So in France, if you play a game of dice, so you're gambling on the dice, if someone had a weighted dice, so that it was going to come up with a 1 or a 6 or whatever you were weighting it, they called that an English dice. I'm sure we probably called it a French dice, but Laplace was very interested in how you determine whether a dice is English. So he was into probability because of questions like that. Now that's a different probabilistic setup, but the techniques he used when he was looking at that sort of question, which was sort of 1780, he then brought back. He sort of said, well, this was the big, I think, philosophical jump that I believe he was mainly responsible for, is taking that sort of idea of chance, where probabilities had been used not first by Gauss, but by other people, and applied to gambling, to try and work out when games were fair or not, and taking those same ideas and applying them to measurement of the heavens. And he's famous for Laplace's determinism, right? It's a bit odd. He's really the founder of stochastics in modeling. It's odd that he's famous for Laplace's determinism. Laplace's determinant says, oh, if I knew everything about the universe, I could predict the entire future of the universe. And since the universe is driven by Newton's laws, I should be able to do that. But he never said that. He set that up. He said, if this were true, then I would be able to do this. But that's impossible because there are so many unknowns. And so we must be probabilistic. So ironically, everyone says Laplace's demon, that's a demon saying if this was true. But no, it's a setup. He's saying, don't be stupid, of course that's not true. So in practice, I don't know the state of the universe. And the way I deal with the unknowns is probability. And that's what we're doing here. The unknown is the corruption to the measurement. And Laplace knew this 200 years ago. We do nothing, I believe, in machine learning that's more advanced philosophically than that. And he took these ideas from gambling and he applied them in the regime of regression. Of course, they didn't call it regression. They just thought of it as prediction, I suppose. So, but how do we, so this is the likelihood of an individual point. So this is the distribution of a single point, yeah? So if we know the input and we know M and C, we can use this. So these are the knowns and this is the unknown. We can use this to predict what we're going to measure for Y. So what Laplace said is that we should maximize the likelihood. He didn't quite say it this way around because the term maximum likelihood wasn't invented yet. He used Bayesian justifications, which we'll come to later. But fundamentally he said we should maximize this function with respect to the parameters we're interested in. Yeah? Thanks, Martin. But this is a function for one data point, so what you need to do is extend that to multiple data points. And here's another key assumption. So first of all, we've assumed that the Gaussian noise is drawn from the noise is drawn from a Gaussian. The other thing that's implicitly in what we were writing down is it's drawn independently. This is the big assumption in statistics, IID. Your data is IID. I think that's a terrible term. It's a terrible, terrible term. Because what you're really saying is your noise is IID. And this is where you're making the assumption. You're saying that the distribution of these corruptions is IID. So you're not really so much saying that, well, you're saying Y is IID given M. So it's independent and identically distributed if you know M. If you didn't know M, it wouldn't be independent anymore because they're all related through M. I didn't draw this very well. What you're really saying, though, is this guy, I should have kept where we define the noise distribution. It's the problem with putting too many animations in your slide. This is IID. The difference between your model and the world is IID, yeah? Now that gets confusing later because when we do Gaussian processes, it's all about correlation. Because we start being probabilistic about this part, and that induces correlations. Of course data's correlated. How dumb would it be to say that your data is IID? that it's independent. If all your data is independent, then there's no relationship between any of the data points. You can't learn if they're identically distributed and independent. That's uninteresting. And it is uninteresting because it's the noise. You're specifically not modeling that part. So it's a really sloppy thing to say that my data is IID. What you're saying is really that your noise is IID. And you're saying, given your model, you expect the residuals to be independent and identically distributed. That's what you're saying. And that's really important because otherwise it gets confusing when we go to Gaussian process models and it turns to be all about correlation. So the data set likelihood is given by independence across your data points, but that's because the noise is independent. I should really have had epsilon vector, probability of epsilon I to emphasize that. I wasn't thinking when I wrote the slide. So this is the likelihood for the entire data set, a product across all those individual single point likelihoods. And what we want to do is we want to find the most likely parameters, the parameters that make, I shouldn't say most likely parameters, because it's slightly incorrect to say that. You want to find the parameters that make the data the most likely. That's the correct way of saying it. It's not the likelihood of the parameters. That's a bad thing to say. It's the likelihood of the data given the parameters. And we're trying to find parameters that make the data more probable. So it's a sort of sensible thing, that we're going to maximize this function to make the data as probable as possible. Any questions there? How many people have sort of seen linear regression introduced in this way, through probabilistic? I think not many. I think it is the only way to think about linear regression, because it's the only one that makes explicit your assumptions. I mean, you can do it by least squares, yes, you can do it by here's an error function, which we're going to come to the error function in a moment, but then that doesn't actually explain why that's the right error function. There are other interpretations for line fitting. So there are frameworks like empirical risk minimization, where you're trying to minimize a cost. And the interpretation of the cost function is some cost you will pay if you get your prediction wrong. That is very much not what we're doing. We're trying to fit a model, and we're ignoring cost. The justification for that is given by, if our model is correct, it turns out we don't need to care about the cost. Now, our model's never correct, so that's never true, but that's the framework we're using. We're going to fit a model, and we care about the cost of error at a later date. So the cost function that we see is derived from the probability distribution, but you could introduce least squares by just writing down a cost function right from the get-go and minimizing that and saying, this is the cost I'm interested in. That's not what we're going to do.
Can you explain the likelihood of a single data point using our example of the marathon?
Yes, that's a good idea. So, let's see. Let's get a good... maybe we have to go forward to where we fit the... I don't want to go through that yet. Let's go through... I want a line and some dots. So we'll pretend this is the marathon, and we'll pretend the marathon's getting slower. So here's the marathon time in 1984, let's pretend. And what our model was saying is that the mean of the Gaussian is given by this line. So the mean of the Gaussian is a function of x in this case being time, which happens to be increasing. So the likelihood says, what you have to think of is around this line is a little Gaussian bump of a fixed variance that's coming out of the screen like this, yeah? And at this point is a certain distance from this line, and the likelihood is given by basically the square of the distance, the actual distance between the point and the line being the argument of the exponential in the Gaussian distribution. So the likelihood at that time is given by so whatever that little distance there is given by the y observation for 1984 minus the m times the x for 1984, which is 1984. So let's just put that in. 1984 minus c, because it's minus f of x, and f of x is mx plus c. squared divided by 2 times the variance. So the variance is giving us a scale in this direction of how much corruption we expect, exponentiated, and then the normalization constant of the Gaussian. So it's not very clear. The normalization constant of the Gaussian is 1 over square root of 2 pi sigma squared. So this is what we can compute for that point. We know his distance away, and we just need to negative square, well, it's the square distance negative divided by 2 sigma squared, exponentiated divided by 1 over 2 pi sigma squared. So what can change? So what do we want? What are we trying to do? We're trying to, if we only had one data point, yeah, and we were trying to fit a Gaussian to it, it would say, oh, the mean should be where the data point is, yeah? Because it can make that term 0, yeah? So it would put the mean bang on the data point, and then it said, oh, now I've got that term to 0, what should I do next? Well, this term being 0 is going to mean e to the minus 0, so that's 1. And then in front you've got 1 over square root of 2 pi sigma squared. Sigma squared's at the bottom. So what's it going to do with sigma squared? Anyone? To increase this term, 1 over sigma squared, this, or 1 over sigma this term behaves like. So it's going to do what to sigma? It will reduce it, yeah. It's going to make sigma 0. So the form of the Gaussian you'll get is actually a delta function. And the likelihood will be infinite. You can't fit a Gaussian to one data point. But it's not permitted to do that when you fit. That's the most likely you'll get, is that you'll get a sigma squared of 0, and you'll get the mean such that it's right on that point. But that's not going to happen, because there are other points that it's trying to model as well. That will happen if you use just 2 data points, actually. Because then it can't estimate the noise. It'll just assume the noise is 0. Sigma will go to 0. But for any situation like this, and we'll come back to that when we look at underdetermined systems, then you're going to get a compromise between trying to fit this line through the mean, or through this data point, but you've got to try and fit it through this data point too. So this is why you get this effect that the line sort of moves towards the data. Yeah? Any other questions there? Okay. So this is giving us this product over Gaussian densities. So for that one individual point, we're trying to fit the M and the C such that it's correct, but we're compromised because we have to do that for all data points. So there's a product across all data points, but what we can do with this product is we can actually bring it inside the exponential, yeah? So that's what I'm doing there, and raise this coefficient at the front to the n over 2. Yeah, so that was square root before, square root, but product n times is giving me an n over 2 term there, or to the power, and 1 to the power of n over 2 is 1. And then the product of the exponential, but I can bring the product inside the exponential as a sum. So that's my likelihood of the data. Now what's this term look like here? It's the sum of squared error. Yeah, so that's something people who've done linear regression will no doubt be familiar with. This is the sum of the squared error. So it's the negative sum of the squared error divided by the variance, 2 times the variance, exponentiated and times by some sort of normalizer term. Okay. Now, I don't have the slide on this, maybe I should have included it, but actually we will work with the log likelihood. So what we want to do is we want to maximize this. We want to find the M and the C that makes the data most likely, a compromise across all data. But instead of maximizing it directly, we're going to maximize its log. Why can we maximize its log? Well, log's a monotonic function. So I have to think where log goes. So log at log of 0 is minus infinity, and then as you make log of positive, log goes up monotonically as you increase. Yeah. So it's a monotonic function. Now, for any monotonic function, if you transform something you're trying to maximize, f to log f or whatever, you get some relationship that's monotonic, and the ordering of any set of parameters theta doesn't change in the monotonic function. That means that maximizing the likelihood is always the same as maximizing the log likelihood. So instead of maximizing the likelihood, what we tend to do is maximize the log likelihood. We can do that for any monotonic function. And what it allows us, one reason we like to do it is because it actually makes things a bit easier to differentiate, which is what we're going to have to do to maximize. Differentiating through a product, which this is typically not nice. So differentiating the exponential means that you have to bring down that sum around the front and you've got this thing, you'll have an exponential left in. By taking the log, we've got a quadratic form here. And differentiating the quadratic form is just going to result in a linear form in M and C. It's going to be very easy to solve. So we work with the log likelihood and we do maximum log likelihood. So these terms are, this one's constant, it just scales with the data. This one's only dependent on sigma squared, and this one's dependent on the data fit. Sometimes people think of this as like a capacity term, and we'll come back to that when we do multivariate Gaussians, because we're going to look at the multivariate form tomorrow. And you can think of this as a data fit term. But the only term people typically care about when they're doing least squares is this term. This is the least squares term up to 2 sigma squared, yeah? So, maximum likelihood is this is a more recent thing, but it's shown to be consistent. What do we mean by consistent? If the data was genuinely sampled from the model we've specified, then what you can show is that as you go to infinite data, you will recover the correct parameters. So, if the data was generally sampled from a line with M and C as the sort of scale and the offset and had a variance of sigma squared, then if you take the data to infinity, then you will recover the correct parameters. And that's proven through using the law of large numbers and one of the justifications of maximum likelihood, which is based on minimizing the KL divergences between 2 distributions. I'm not going to go into the details of that. I think I've got some reading material on that in one of the slides. It's a mainstay of classical statistics that maximum likelihood is consistent in this way. I don't really care so much because of 2 things. One, I'll never have the correct model if I'm working with real data, pretty much. And 2, no one ever gives me infinite data. So that's one reason why we end up using Bayesian approaches, but that's the justification for maximum likelihoods. So this is actually, sorry, I should go forward to here. What we can think of, instead of, it's convention in optimization to never talk about, optimization people must be pessimists because they never talk about maximizing things, they always talk about minimizing. So you've got a choice between thinking of maximizing benefit or minimizing cost, yeah? Now, optimization people, in the field of optimization, they always talk about minimizing a loss or a cost. So when we talk about optimization, I typically switch to an error function, which is the interpretation that Gauss and Laplace would have had on something like this, where the error function is given by things which are parameterized in the way I'm interested in. So what we do, instead of maximizing the log likelihood, we minimize the negative log likelihood, and that has this form. And then if you remove the sigma squared bit, which is associated with the Gaussian, that's just the sum of squared error costs, yeah? So you can see this is how you get the least squares. It's coming from the argument of the Gaussian. Whatever you put in the argument of that distribution, the sum over data comes from the independence assumption about the noise, that the noise is independently distributed. And the fact that you get the argument of the Gaussian is because it's e to the argument and the e is removed by doing the log. So that's why it's very nice to use the log in this situation. So learning proceeds by minimizing this error function for the data set provided.
On that one, you're saying that the difference is that there the noise is ID.
Is what, sir?
Is independent.
Yeah.
And so that's why you don't have the other parameter which we had as over 2 log.
Sorry, yeah, the one thing, yes, sorry, there were two parts. Yes, I've removed that because it's not dependent on sigma squared, m or c. So it's dependent only on n, the number of data. So when I'm looking for the parameters, I'm not that worried about it. Sometimes people also remove that from the error function as well. That you don't see that in the least squares error function because you're only really trying to fit m and c. You don't care about the variance, yeah. Okay? So, learning proceeds by minimizing this error function for the data set provided. Now, I'm going to do an exercise in futility. This next little bit of exercise is designed to make you understand why linear algebra is vital. Because what we're going to do is we're going to minimize this cost function with respect to m and c, but we're going to do it without using linear algebra. So we're going to come up with a couple of equations for doing that. So we're just going to focus on the m and the c. And then we get the sum of squared errors function. Yeah? So where f of x is given by this. So what we need to do is minimize this cost function. Now we know at the minima the gradient will be 0, and the technique we typically use is to find the point in M where the gradient is 0 by first differentiating the cost function. So to differentiate this, I get the 2 out the front with respect to M. So we're differentiating the whole function, always brings the 2 out the front, and I just get that linearized. And then I need to differentiate within the bracket. And because this is across a sum, so the sum just stays on the outside because it applies to every term. When I differentiate within the bracket, if I differentiate with respect to m, I just get xi out the front. So the 2's coming out, so I get minus xi out the front because it's appearing in here. So this is the gradient of that cost function with respect to m. So to find the minima, the point at which that gradient's 0, because what we've got is a quadratic. This is a quadratic in M, so quadratics look like this, and we're looking for this point here. So we're looking to find the point at which the gradient's 0, because that will give us a minima. So writing out all the terms in that sum like so, I can reorganize and find that M is given by the sum of all the yi's minus the c. That seems to make sense because c is like an offset, times xi divided all by xi squared. So that gives me a formula that I can now use to set m. Rather problematically though, it requires me to know c. So let's try finding c then. So we'll do the same thing. We get a very similar equation apart from no x here. And we rearrange again. So that should be mx in there, not cx. And we find something very similar, but with yi minus mxi in here. So the c is given by something that's dependent on m, not c, m. So these two things are interdependent, which is annoying. So what we're going to do, in fact, so this is the correct equation here. So what we'll do is we call our estimate for c at any given time, c star, and our estimate for m at any given time, m star. We can do the same thing for sigma squared, and we can get an estimate for sigma squared. So what we're going to do is estimate c, given an initial guess for m. Or in fact, we're going to do it the other way around. We'll estimate m, given an initial guess for c, and then we'll use our estimate for m to make an updated guess for c, and then we'll use our guess for c to update guess for m. Okay, so that sounds a little bit complicated. So what we're going to do is draw what this error function looks like in 2 dimensions. So this is a quadratic, so remember it's the sum of yi minus mx plus c all squared, sum of I equals 1 to n. So this is a quadratic. It's a quadratic in m and c. And what I'm plotting here is the shape of that quadratic in the space of c and m. So we've got m along this axis and c along this axis. Yeah? So this is the shape of the error function. Since we plotted it, here's the right answer. Straight away we can see that. But of course, in general, we can't see it. In higher dimensions, we can't see it. So what we're going to do is we're going to start with that strategy where we start with an initial guess for C, an initial guess for the M. I've just put the M here. And then we're going to update M given in our initial guess for C. So what we're effectively doing, because we're keeping C fixed, is we've got a slice through this. This is a Gaussian bowl. These are the contours of a Gaussian bowl. And we're taking a slice through this parameter, and we're moving into the middle of the Gaussian valley. Yeah? Does that make sense? That's our update for M. And now we've got, given that update for M, we can now try and update for C. So now when we do C, we're taking a slice in this direction, and we're going to try and find the minima in this direction. Every slice we take through here is just a quadratic, yeah? So this is just a bunch of quadratic ribs. It looks like, I don't know, a Viking boat or something. So, but the twisted one, so all the ribs are along here, and we're just minimizing along each of those ribs. So when we minimize in C, we drop down a little that way. And then we do the same in M, and move across that way. Same in C, M, C. We need to iterate between these. And then I sort of zoomed in. And we start heading slowly towards the minimum. So the first thing we're going to do is we're going to do that linear regression fit by this rather convolved technique. There's actually a straight solution to solving the linear regression, which I'll show you a little bit further on. But this is a common technique in machine learning. It's called coordinate ascent. So it's not the right way to solve a linear regression, but it's quite commonly used in many other areas. So I thought it's a good opportunity to learn the disadvantages. Can you see what the disadvantages of this approach are? Yeah, each time you make a massive move at the beginning. But then once you're in this valley, you're really slow to move down because you're very close to your minima at each step. And this happens because of correlation. So this is very common. These correlations in the models we'll look at, this is actually related to something called the posterior distribution, and it shows this strong correlation in the shape of where this minima is. Why is there a strong correlation? Because the best C is very much dependent on the best M. So if you fix C at some point, then M is trying to move. It's just trying to move like a seesaw to get through the data. Yeah, so it tries to get through the data like that, given a C. But now it's got through the data like that. The best C only moves a little bit. And then it moves a little bit the other way. And then you get this. So what's sort of happening in the fit, I should have drawn the line as it's being fitted, is that you're sort of, we've given it a C that's wrong. And so it's got an M that's wrong. But now it updates to find the C, and it just moves C a little bit, and then it moves M a little bit, C a little bit, and M a little bit, until eventually it gets down to the right position. So we're going to do that for the...
In theory, that right position never comes.
It does come. It will come. It just takes an awful long time. Certainly it will, yeah.
I think it never comes.
It will come. No, it will converge to within a certain tolerance. I mean, in some sense, you're right. If we had full, if we had computers that were completely, had no numerical issues, then because that actual solution would be a point on a completely real line, we would never get to it anyway. But fortunately, computers are finite in their precision, so you will converge to the solution to within a precision eventually. And that's true of many machine learning algorithms, that you converge to a solution within some precision which is typically given by the numerical accuracy of the computer. So that's what we'll try now. Now the first lab session involves doing this on the marathon data. So do people all have the I've lost my mouse. Here we go. Have people got the lab sheet? So it's available from this address here, ml.dcs.chef.ac GPRS lab 0. Now, we're using this as a sort of introduction to Python. How many people have used Python before? Not many. Just 1, 2. Come on, computer scientists, be with me. we're going to tomorrow do more stuff in Python with Gaussian processes. So we're kind of, wouldn't necessarily, if you wanted to do linear regression, there's many different ways of doing it. But we're trying to use this as part of an introduction to Python. I'll zoom in a little bit on the relevant part of the lab. So what I suggest happens is, first of all, let's stop the recording. And then we'll split into groups that we're going to do, where we'll